Alright, so last time we were uh, discussing Arzela-Ascoli theorem. It describes compact subsets of a of the complete metric space of continuous functions on a compact metric space, right? Of course, we know that a compact set is nothing but complete and pre-compact subset. So we have to just this theorem just characterizes pre-compact subsets. Pre-compact subsets of function spaces are subsets which are bounded and equicontinuous. Equicontinuous means that the functions are continuous with respect to the same delta. So equicontinuous is the following. A subset E of a function space Cx is called equicontinuous if for every epsilon there is some delta, so that uh, this delta works for all the functions in this subset, okay? Which means whenever x and y are close to each other, delta close to each other, then their images are epsilon close to each other under all functions in the subset E. Here we take X to be a compact space, therefore a continuous function and uniformly continuous function on X are the same, okay? Any continuous function is automatically uniformly continuous. Alright, now let's see the proof of this theorem, Arzela-Ascoli. It is clear that we have to prove just the first statement, because once we show that equicontinuity is equal to boundedness and equicontinuity, then compactness will be equal to being closed, bounded, and equicontinuous, because Cx is a complete metric space. Therefore, a complete metric space of Cx is just a closed subset. Okay. Now, for the first statement, first assume that any questions so far? First assume that is pre-compact. Then we must show two things. First is bounded, and second is equicontinuous. Well, we already proved earlier when we discussed compact metric spaces that a pre-compact set is necessarily bounded. Okay. One is proved earlier while when we discuss sequential compactness, actually. Compactness. So I will omit that. We already proved that. For equicontinuity, we will proceed as follows. Okay. So we must prove is equicontinuous. All right, so given epsilon positive, I need to find a delta which will work for all the functions in the set E. All right, and what we know is that is pre-compact. All right, now consider the balls, consider the open cover, the open cover for E, this open cover, B F epsilon over 3, okay, F in E. I just take epsilon over 3 ball around each function. Of course, you know, each function is contained in one of these balls. Therefore, they form a open cover for E, right? But since E is pre-compact, okay, since E is pre-compact, finitely many of these balls cover E, right? E is contained in finitely many of these balls. So 1 epsilon over 3 F, let's say K epsilon over 3 for some F1 Fk in E, right? This is precisely the definition of being equicontinuous. Sorry. What? Pre-compact, right? Whenever an epsilon given, you may find finitely many balls. Actually, I shouldn't start like this, right? Whenever epsilon is given, there are finitely many. I shouldn't write like this. I should be careful. Okay, given epsilon, since is pre-compact, and epsilon over 3 is positive, there are f1 up to fk so that E is contained in these balls. Okay. Well, since xt is compact, each fi, which is a continuous function, of course, is indeed uniformly continuous. And therefore, thus, there is delta I positive so that xy are delta I close to each other implies f of x f of I x fi of x minus fi of y is less than epsilon over 3. So I work with the same epsilon over 3. Since this function fi is continuous, there is such delta I. Well, I have only finitely many Fi's, right, in this open uh, cover. So let delta to be the minimum of these. Now we claim that this delta will work for all of them. Well, it works for all of them, of course. Then delta is less than delta I for all I from 1 to k. Now, uh, if f is in E and xy in x with dxy less than delta, then I have what? Well, since f is in E, f is in one of these balls, right? There is some I from 1 to k, so that f is in this ball, and hence we have what? Uh, the distance between f and fi is less than epsilon over 3. In particular, we have the following: f of x minus f of y, which is equal to, uh, which is less than f of x minus fix plus fix minus fiy plus fiy minus fy. All right. Well, the first term is less than epsilon over 3 because the distance between f and fi in the supremum metric is less than epsilon over 3. So the first term is less than epsilon over 3. This is less than epsilon over 3 because of the choice of x and y. X, y are delta close to each other, therefore they are delta I close to each other, and in that case this expression is less than epsilon over 3. So the middle term is less than epsilon over 3, and this is less than epsilon over 3 because again f is in this ball. So f and fi are delta epsilon over 3 close to each other, so which is delta. So this means what? F is uh, uniformly continuous uh, with the same delta. So what we have obtained is the following: then given epsilon positive, I found some delta. Of course this delta is positive, right, because it is the minimum of finitely many, right? The crucial thing is that, why this doesn't work for infinitely many FIs. Well, I have only finitely many FIs and finitely many deltas, therefore I can choose their minimum, okay, which is still positive. And whenever f is in E and xy are delta close to each other, this distance is less than epsilon. So hence Right, F is an arbitrary element E, hence E is equicontinuous. Okay. Is there any questions so far? So we proved one direction that if it is pre-compact, then it is bounded and equicontinuous. Now we have to prove the other direction. Okay, so let's start proving the other direction. Now we assume is bounded and equicontinuous. And we must show is pre-compact. All right. Again, by the definition of pre-compactness, we have to start with an arbitrary positive epsilon. So given epsilon positive, okay. First, since E is equicontinuous, since epsilon over 4 is positive and E is equicontinuous, there is some delta positive so that uh, for any f in E and uh, xy in x with dxy less than delta, we have what? We have the following. This distance is less than epsilon over 4 for okay, we have this. Whenever x and y are delta close to each other, then this is less than epsilon over epsilon over 4. This is true for all f. Okay, so we have a delta which works for all of them, for all the functions. Okay. On the other hand, we have this. Since xt is compact, it is pre-compact, and there are points x1 up to x, let's say, rho in x with the following. X is contained and therefore is equal to this union. x1 delta x rho delta, right? Any compact set is pre-compact, and pre-compact means x is pre-compact means whatever you give me a positive number, I can find finitely many balls with that radius which covers the whole metric space. Okay, I have this. So any point in X is delta close to one of these points, right? That's the important thing. On the other hand, E is bounded, right? We know that E is bounded. Therefore, the whole subset E is contained in some ball, and I can choose the radius, the center of this ball, any function I want, and I'll choose it the following function. Let O or 0 be the 0 function. So whatever you give me, it gives the 0 the real number 0. Okay, 0 function. This is clearly continuous, of course. Uh, Clearly this is a continuous function, so it's in the metric space Cx, and since E is bounded, uh, there is some m positive, so that E is inside the ball with center O and radius m. Maybe I should. Okay, yeah, right. So around this function, the 0 function, I can draw a ball with some possibly big radius which contains all the set E, the bounded set E. Of course, this ball and the balls are here are completely different objects. This is a ball in the metric space X. This is a ball in the function space Cx. Okay, I use the same notation, but from the context, it is clear what I mean. All right. Well, this means what? So for any x in X and f in E, right? Uh, okay, oh, sorry. So we have what? Distance between f of x and the 0 function is less than m, but this is just 0, right? This is just 0. So this means f of x is less than m. So let me say right like this. Okay, for all x in X and f in E. So that's the conclusion. These functions are bounded kind of uniformly. Okay, there is a bound which works for all of them. Okay, all right. Now I'll do one more okay construction. Consider this part of the real line minus m plus m. Of course, this goes like this. Choose a partition. Partition. Let me say P C1, C2 up to CQ of this interval so that uh, Okay, I should start from 0 maybe. Yeah, so that we have this. Uh, minus m is xc0. I have xc1, xc2, and we go up to xq, which is m, and the distance between two consecutive xi's is what? And xi plus 1 minus xi, right? These are all positive numbers, but this is less than epsilon over 2 for all I from 1 up to uh, no 0 to q minus 1. Okay, so I have the following. This is xc0, this is xq, and somewhere here I have xi and xi plus 1, and this distance is always less than epsilon over 4. Okay, all right. Okay, all right. What else? Now, now for each f in E, okay, uh, and uh, f of xi, let me say, is inside one of these balls. I mean, in here, because all the functions have values between minus m and m, right? I have this. And what are those this xi's? Xi's are, remember, the points which covers our metric space. Uh, delta balls cover the metric space. So I have finitely many such points, x1 to x rho, and I am looking at this value. This value is between these two numbers. Therefore, this value falls into one of these intervals. Okay. So I have what? This thing, uh, and thus, okay, there is some ck, cky, so that uh, f of xi minus cky is less than uh, epsilon over 4, right? Because this number f of xi is here, so it will be either here or here, but it will be between uh, uh, two consecutive ones, and whichever, so if it is here, the distance between f of xi and this ci, so I can choose, for example, in this case, ki to be I or I plus 1, or if it is here, ki will be can be chosen as I plus 2. Okay, all right. Now, so for any f, there is a uh, uh, q tuple of points. Hence, hence, for any f in E, there is a okay q tuple let's say k1 k p maybe I should say p tuple where p is less than q, so that so that so that we have this, so that f of xi minus xki is less than epsilon over 4. But okay. Yeah, I should write like this. Xi k1, Xi k2, Xi kq. Okay. The reason I wrote not q tuple but p tuple was because of the following. You see, some of these ki's could be the same, right? Maybe k1 and k2 are the same. I don't know. Maybe this function is just constant function. So all of these xi's are the same. In that case, if you write the set notation, this set contains only one element, not necessarily q distinct elements. Okay, that's why one has to be careful. All right, I have this. Okay, what else? Well, maybe I write like this. All right. Now, how many such k tuples or q tuples I have? Well, there are q plus 1 xi's, and I choose q of them. Well, and but they don't have to be distinct, right? For each of them, there is q plus 1 choices, right? For each of them, there are q plus 1 choices. This could be so xi0, xi1, q, and the same for all of them. Therefore, uh, since okay, note that there are at most how many? So I choose q of them among how many? Q plus 1 of them. So I have q plus 1 to the power q such q tuples. In particular, there are finitely many of them. Okay. Now, and for each such tuple, okay, uh, let I be the set of all these Q tuples, and we know that each such tuple, K tuple, Q tuple, sorry, comes from a function, right? Each of these, Q tuples obtained from a function. Now, for each such Q tuple, let's choose a function. Okay. Okay. Now, for each Q tuple in I, choose a function. Okay. Function G, so that of x minus xki is less than epsilon over 4 gxi. Okay, for all I from 1 up to okay. I guess I lost internet connection at some point, right? But now you hear me, I guess. Okay. Oh, I see. Here we have only row points in X. Therefore, yeah. I have to be row points. Therefore, uh, okay, how many eyes I have? I have only I from 1 up to row. 1 up to row. Therefore, I have only row tuples. Yes, because there are only row xi's and row tuples. So I have here this row tuples, not Q, but row tuples. And for each row tuple, I choose a function like this. Okay, and I have this. All right. And then we do what? Well, for each row tuple in I choose a function. Of course, you know, the cardinality of E is finite. It is at most this number. Therefore, in particular, the set, let's say A of such G's, these functions, is at most uh, the cardinality of I is Okay, cardinality of I. Okay, it is this. Because for each row tuple, I choose a function, right? So there are at most this many functions. Okay, now let f is in E. Okay, f is in E. Then, uh, of course, remember, uh, for any E, I have a row tuple, right, like this. Okay, so for any F, I have such a row tuple, and for any such row tuple, I have another function G, right? Uh, so that G also satisfies the same inequality, right? So we have the following. Uh, let Then there is uh, a row tuple ck1 ck row and G in A. Okay, G in A. Uh, so that we have this, both f of xi uh, xi is less than epsilon over 4, and g of xi xi ki is less than epsilon over 4. All right. Okay, now finally uh, f of x minus g of x. Now for any x in x, this x, choose some I from 1 to row with x is in bxi delta. Remember, my metric space, since it is pre-compact, it can be written like this. So whenever you give me a point, it lies in one of these balls, right? So it is delta close to uh, one of the centers. Yeah. And thus this distance f of x minus g of x, this is less than f of x minus fxi plus fxi minus gxi gxi uh, minus no, I have to be careful. Okay, f of xi minus ki cki plus cki minus g of xi, and finally g of xi minus g of x. Okay, well, uh, x and xi are delta close to each other. X and xi are delta close to each other, and f is uniformly continuous with respect to this delta, and the distance between x and fxi is less than epsilon over 4, right? This is because of the following. Whenever x and y are delta close to each other, then this distance is less than epsilon over 4. And in our case, x and xi are delta close to each other. Therefore, this is less than epsilon over I. Well, this is less than epsilon over 4, this term, because of this. And similarly, this tells us that this term is less than epsilon over 4. And g is also a function in E, therefore this distance is less than epsilon over 4. The same reason this is less than epsilon over 4. So what we have obtained is then f of x minus g of x is less than epsilon over, no, is less than epsilon, so that f belongs to this ball. F is an arbitrary element, right? F is an arbitrary element. F was an arbitrary element. Epsilon was arbitrary also. So this means what? Hence, E is contained in the union of B, G, epsilon, and G belongs to the set where A is a finite set. Finite subset. So, subset of E, of course. So what we have seen is that E is contained in finitely many epsilon balls. In other words, E is what? Precompact. Okay, and this finishes the proof. Okay. Any questions so far? All right. Let's give a break. After the break, we may talk about this. Maybe I can give you one example. Okay, so let's have a break.